In other videos, we have looked at PERT, Program Evaluation Review Techniques, and we've created a precedence network to find the critical path and determine how long a project takes to complete. And you can do some of this in Python. So if you want to look at PERT and precedence networks in Python, go to drstephpowers.github.io/mgmt-in-python. And there's a link in the description for this video and at the top of the screen. Once you are here, we are going to go to where it says Project Management, PERT with probabilistic durations. So we're going to look at the scenario where you have different possible times that different activities could take. So there's a probability of different durations or different times for each activity, and that can result in some uncertainty. And so we can use Monte Carlo simulations to look at that probability of completing at a certain time in Python. So click here where it says PERT with probabilistic durations. It'll bring you to the Python worksheet. But in order to actually work on this Python worksheet, you need to click here where it says Open in Colab. This little icon doesn't always appear properly, so if you're not seeing that icon, then click on where it should be, the little square that might appear there, and it's going to take you into Google. So we are using what's called Google Colab, and Google Colab is an application in Google. In order to run the code that you see here, you will need to sign into your Google Drive account. And if you want to be able to edit the code, change it, write your own, you'll need to copy it to your Google Drive. This gives you your own copy that you can amend as you wish. So I'm just going to switch over here where I'm logged in, and that way we can run through it. So first we want to create an image that represents our precedence network. And so just to give you an example here, you saw this probably in the previous video where we talked about precedence networks. Here we have a precedence network that is an AON version. So activities are on the nodes. So what you see here is the project of building a house, and our nodes, here we have our circles, they represent the activities. Design the house, order the materials, select the paint, and so on. And the key with the precedence network is it shows you that in order to lay the foundation, we must have first designed the house. And in order to select the paint, we must have ordered the materials and we must have already laid the foundation. So that particular activity, activity 5 here, is dependent on both this activity and that activity. And both of these activities are dependent on this activity. So that means the time it's going to take to finish this project is dependent on the fact that we have done all of these other activities. Now notice it's not a straight line, which means that we can do some of these activities at the same time. So determining how long it takes to do this project is not simply just adding up 3 months for this, 2 months for this, 1 month for that, and so on. We can actually figure out the quickest we can finish the project by finding what's called the critical path. That is the route through this network that takes the longest time, because that's what's going to slow down the process. So notice we could go 1, 2, 4, 7. That is one route. 1, 3, 4, 7 is another route. 1, 3, 5, 6, 7 is another route. 1, 2, 5, 6, 7. All of these activities must be done for the project to be completed, but it is the route that is the slowest that is going to limit you. So, for example, after we've designed the house, some of our workers can be laying the foundation while others are ordering and receiving materials. Laying the foundation takes longer, which means that you'll order and receive the materials, and then you kind of wait for the foundation to be finished before you select the paint. So you start these, or you could do these about the same time, and there's what we call slack or a buffer here, in that there's a little extra time to order and receive materials because the other activity you're doing at the same time takes longer. And so activity 2, laying the foundation, is going to be part of the critical path that's slowing down how quickly we can finish this project. Well, if we're doing this in Python, we can create that visual using what is called Schem Draw. And you need to install it. It's not already built into Google Colab. So we use this command here, pip install, and it is going to load in that package. This package is created to make visuals to show things like circuits. It has lots of functionality, can create all kinds of different images. We'll use it later for creating process flow diagrams if you're not doing them, say, in Microsoft Visio. So we're waiting for that to download. And we click the little play button that you see to the left. That runs the code. And when it stops turning around, it means that we have done that. And it told us it took 26 seconds for that to install. Then the next thing we need to do is, now that we've installed it, we need to import it. So we need to get it into working memory so that we can start using it. So we're going to import that Schem Draw. And particularly we want a sub package that's within it called flow, because we're essentially going to use the shapes that are used with flow charts. So we will import that, both the bigger package and particular the flow part of it. Now, when you do a Schem Draw drawing, you are basically saying we're going to do a Schem Draw drawing. That's the first line. And we're going to call the drawing we're creating D. So you could pick a different letter if you wanted it, but we need to basically give it a name. And that way, as we add images to the drawing, we attach them to the drawing by saying, let's add them to D. So we're going to create a drawing. We're going to call it D. And we're going to configure that drawing to have a font size of 8. This changes how big the words are. And then what I recommend if you're doing the Schem Draw is that you start with your activities. So here we have those same activities that you saw, and here we have the labels. So we're going to have a start. We're going to design for 3 months. We're going to lay a foundation for 2 months, receive the materials for 1 month, build a house for 3, and so on. So what we're doing here is we're adding each of these images, and we've given them a label, A0, A1, A2, A3. You need to give them a label because we're going to attach arrows and lines between them, and so we need a way to say, connect this to this. And then what we're doing is we're creating boxes for most of these things, and for the start and finish, we're using the circle icons, and so the label here is start. So we're doing flow, and we are pulling from our package flow. We are pulling the start icon, and we're pulling the box icons. And we are saying the width of those boxes and the height of those boxes. So we've specified that here. We just want them to be wide enough so that the words fit. And we pick a height as well. And then we put our labels. So here you can see this is the same. If I go back to this image here, start, and then we have our activities and how long they take. So we have build a house, which is activity 4, and it took 3 months. So if we go back here, you can see activity 4, we'll call it A4, build a house, 3 months. So if you start here and you run this, what it does is it just creates all of your boxes. Okay. Now we want to connect those boxes to show that flow, to show that precedence network. And so what we do then is we can then take our activities and start to add arrows in between. Okay. And I have a completed version here that you can see on yours, but I'll just show you as we add one piece at a time. So I'm going to add from the flow package, I'm going to add an arrow. That's that flow.arrow. And the arrow is going to go to the right. So we're going to go from the start to the right. And the length of that arrow is going to be the number of units divided by 3. We're just trying to make this a little tighter. And then we want this to come from the middle of the start. So this XY, think x-axis and y-axis, we're going to go from A0, that's our start, and we're going to come out of the start on the east side, north, east, south, west. We're going to start on the east. And by saying XY equals A0 east, we're saying from the center of this. Okay, if you don't specify that XY A0 dot east, then it will put it on an edge and it will decide where. And then we have 2. So where is this arrow going to? And it's going to go to A1. And A1 is going to be here next to it. And so we want them to connect where A1 connects on the west side. And we're going across the x-axis. So if you're going to the right or left, you should have 2x. If you're going up or down, you should have 2y to help it identify the fact that it's going to be connecting on the vertical or horizontal axes. So I can hit run. And you'll notice here I've just added that one line for the arrow. My start goes to A1. The arrow joins from the center. It goes across the x-axis. It goes to the right. It connects A0 to A1. And so you can start to flesh out more and more of your graph. So I'm just going to pull another one here. So if we go back to our original design wants to split. We want to go from A1 to A2 and to A3. So we need one arrow to go one direction, one arrow to go the next direction to connect them. So we're going to have then from A1, we're going to have an arrow go up, and it is going to connect to A2. And it is going to go from the center of A1 on the north end of this image. So basically right here, it's going to go up and it's going to connect to the south of A2, the bottom of the box, and it's going to be a vertical connection. So notice that as I add this, start to A1 to A2. And you can see I'm starting then to fill out that network. And I'm just going to take more here. So now we want to go and we want to have it so that we go from A2 on the east side over to 4. And that's because on the image, we have this connection here. Okay. One of the reasons we run it first with just the activities is that depending on where you plop down this command, if I have plopped down this command here and it says connect to A4, it'll give me an error because it says, well, A4 doesn't exist. Okay, but if I run this first with just the activities, it then knows that there's an A4, and so then I can put this line of code in all kinds of different places. So notice if I run it now, I now have start to A1, A2, and it doesn't quite know what to do with A3, so it's connecting over here. So I need to specify where does this A3 live? I know it's supposed to be connecting to A4, but it doesn't know what to do with A3. So we can take then, I'm just copying here from this final one. You'll notice these code lines are all the same. They're all flow arrow. This one is going to go down from A1 from the south part of the box, and it's going to go 2 on the y-axis, so vertical, A3 on the north end. So let's rerun that. Okay. How are we doing? So here we have 0 going to 1 on the right. We have A1 going to A2 on the up. We have A1 going to, supposed to be going to A3, going down. Let's just rerun this here. See why it's confused. A1 to A3. It should be going A1 down to A3. 0, 1, 2. It's a little confused because we've mentioned 4. It doesn't know where 4 lives. So let's try putting in the links to 4 and see if it's still complaining. Let's see. All right, so here we have A4. Skim draw is a little finicky. Sometimes you'll find, for example, here A3 and A4, it doesn't know what it's kind of screwing it up. So what you can do is you can rearrange the order and you could put A4 before A3. What it really likes is it prefers that you're going in the order that it connects. So start to A1 to A2 to whatever connects here, and keep going. When you start to have the complicated mixing lines, then it gets a little finicky. Try rearranging the order. So now here I put A4 before A3. Start to A1 to A2, then it's going to A4, and it's connecting A4 to, I don't know why A4 is connecting to A3. Let's go A4 to A3. Given the choice, at the end of the day, like if I'm doing a lot of the graphing, like in terms of flowcharts, precedence networks, Microsoft Visio, of course, way faster than trying to do it in Python. And what a mess. Here, let's try this. So this order here. So sometimes you got to fiddle a bit with the order to get it to rearrange. This one here with this order, so I'm just going to take it. Let's do this. Maybe you're better at laying them out than I am. Here, I'm just going to do this, replace half of this. Sometimes you have to fiddle a bit to get it to lay out right. But here we have A1, A2 to A4. It goes down from A1 to A3 to A5, and then it's 6, and then to 7. And we have in our graph here A4 to A7, and then going to the finish. When you do this, if you have cross lines, like if we had, as you could see here, where they cross, you go from activity 3 to 4, activity 2 to 5. Do them last because it causes it to throw your graphs in all kinds of weird places. So you can see here in this code, I've added it at the very, very end. So there's an arc. These are the curved lines as opposed to a straight line with an arrow. We have arcs. This allows for like what you see here. These are arcs. And so if you're running these extra connections between, then putting those arcs at the end will make it lay out better. But the point of this video, as crazy as that is really not about the graph. It's about finding the completion times. How long does it actually take to do this activity? So to do that part in Python, we're going to need pandas as a package. We're going to need NumPy as a package. And from NumPy, we're going to import random. So we're going to be randomly generating numbers. And NumPy and pandas allow you to change the configuration of and the formatting of your data inside of Python and to do calculations. The other thing is we want to be able to plot. So we're going to import matplotlib.pyplot and call it PLT. And we're going to import Seaborn and we're going to call it SNS. So matplotlib and Seaborn are the graphing packages. And so because we're going to create a histogram, show the distribution of our data, we're going to import those as well. Now, the first thing you want to do is create a definition, and this definition is going to say, here's the critical paths for your image. So if we go back here, we talked before that we have A1, A2, A5, A6, A7. That's a critical path. A1, A3, A4, A7 is a critical path. So we want to find all of the critical paths, and here we have, here's 1, here's 2, here's 3, here's 4. So in this particular example, there are four paths, and we want to find the critical one. So we're going to define critical path, and we have activities 1 through 7. And path 1 is A1, A2, A4, A7. Path 2 is A1, A3, A5, 6, 7. So you're defining out all the paths and the activities, because what you want it to do is you want to give it the amount of time that each of these activities take, activities 1 through 7, the ones you see here. You want to give it the times for these 7 activities, and then you want to automate the process so it finds which path is the longest and then tells you when's the quickest you can finish this project. That's what we're creating in this definition. So find the maximum time, find the maximum when you add up the times for these different paths, which path takes the longest. And then because we want to monitor when we start to change how long each activity takes, which path becomes the longest and does that critical path change, that's what this last part is here. It says if path 1 is equal to the max time, then we're going to call that CP equals 1. Otherwise, so else, if path 2 is the max time, then we're going to call it CP equals 2. And this else if path 3 is the max time, then we're going to call it CP equals 3. Otherwise, so the else here, there's no more else if, just else, CP equals 4. So it's basically 4 scenarios. Path 1 is the longest, call it CP equals 1. Path 2 is the longest, call it CP equals 2, and so on. And so we can collect the information as to which path is the longest. And when we do a Monte Carlo simulation, we're going to run this 10,000 times, and we want to see if the critical path is always the critical path. Does it always take the most amount of time? So if you're doing this for your own scenario, you might have more activities. So change this input here. You want this to match the number of activities, and then change the path to match the paths that you have in yours that you would get from your precedence network. Okay, from your graph, figure out how many paths and figure out what those paths are. And so if you need to, you can add a path 5 or 6. Just make sure you add it to here so it's determined as part of the maximum. And then just add more elifs for all those other scenarios. So we would run this. Now I can call this definition and have it output the maximum time and tell me which is the critical path. So my input for this definition are the 7 activities, how long they take. So if I go back and I have no probabilistic, in terms of no probabilities of the times, we know for a fact that designing a house takes 3 months and laying a foundation always takes 2. There's no probabilities here. It's just, here's how much time things take. So then we just enter in 3, 2, 1, 3, 1, 1, 1. The times for each activity. 3, 2, 1, 3, 1, 1. Run that. Output the max time. The time it takes to complete this house is 9 months. The critical path is path number 1, which is A1, A2, A4, A7. Okay. Well, great. But in real life, everything isn't certain. There is uncertainty, and we have to figure out then, what if some of these activities take different amount of time? So here we have 4 of the activities could have some variability. And we have A, M, and B. So A is best case scenario, the quickest we could get it done. M is the most likely time it will take. and B is the more pessimistic, it'll take longer. So I can take this activities, A1, A2, A4, A5, and the different values of A, M, and B, and all I'm going to do here is really define them, and I'm going to put them into a table. To put them in a table, I am going to use that pandas, so PD, and from pandas, I'm going to create a data frame. That data frame is going to have columns called activity A, M, and B, and then I use what's called list and then parentheses zip, and it tells it to take my information from above and format it a certain way. So it's going to create a column with the A's I gave it, a column with the M's I gave it, and a column with the B's I gave it. And it's going to put the activities there, and it's going to create them as columns. So that's what you see here, is that it's just taking this information and turning it into a table. So you can basically keep this as it is written, and if you have, in this case, we wouldn't change any of this, but if you were doing this formula here to create a different table, it's simply the names of your columns here with the quotes around them to make them the names, and here to call them in terms of inputting the data attached to them. We're going to name this table var for variability, and you can see here it says set underscore index activity. So if we didn't do this, it would say here is row 0, here is row 1, here is row 2, and so on. In Python, counts start with 0 instead of 1. So your first row or your first column has an index of 0. We don't want it to say index or row 1, row 2, row 0. Instead, we want to use our labels. We want to use our activity labels. So we're setting the index based on the activity labels we've given it. All right, so let's run that, create the table. So we do all this so that we can pull this information as we do our calculations. So if we have variability in the duration of the activities, we're going to assume a beta distribution. Okay, so we're going to create a definition here and we'll just call it PERT. You can call it something else if you want. And it needs to input A, B, C, and we're doing size equals 1. So it's essentially going to just run it once. And what this is, and you can leave this as here, is that this is doing the beta distribution based on giving it 3 values, A, B, C here. Well, we're going to generate numbers using that beta distribution with our values here, with this our optimistic, our pessimistic, and our most likely. And so if you are doing a beta distribution, you can just take this definition here as it is, and it's going to randomly generate a number using the beta distribution, and it's going to pull from, we give it 3 values. And so the size equals 1 here is just telling you it's going to randomly generate 1 number. Okay, we're ultimately going to do this 10,000 times, but we just need it to generate 1 time for each activity, and then we can figure out how long it's going to take. So here's our definition. Our definition takes the extreme values and finds the difference between them. Alpha and beta are parameters. So if you think about like a normal distribution, the parameters are the average and the standard deviation. For the beta distribution, you have your A and B, or alpha and beta. Okay, we're going to create an empty list. That's what this is, called complete, and we're just going to populate this. So we give it complete equals 0 equals this empty list, and then what we're going to do is we're going to put things in it. So we're going to run a simulation 10,000 times, and we're going to then see for each run, it is going to do this calculation where it's going to randomly generate a number, and we're going to randomly generate a number for activity 1. How long will activity 1 take? So we're going to randomly generating a number using, from our table here called var, It's going to go find the location on that table for A1 and A. A1 and A, then we have the soonest we could complete activity 1 is 1. So that's going to be the A in this beta distribution calculation. Then we're going to go to the table, find on our var table location A1M, the most likely for A1, and it's going to be the B in this formula. And then we're going to find from that variable table the location where A1 and B, so that's the pessimistic, takes the longest time, and that's going to fill in this spot here, C. So we're using a beta distribution to randomly generate a time for how long A1 takes, where the best case scenario is it takes 1 month, worst case scenario it takes 4 months, it likely will take about 3 months. So we're going to randomly generate a number from that beta distribution, and we're going to get a time for A1. We're simply repeating the process for A1, A2, A4, and A5, each time pulling the best case scenario, the most likely scenario, and the worst case scenario. This bracket 0 tells you that when you run this, you just want it to pull the number, not all the extra stuff. So that's all this is here. Then we wanted to do is then take those times for A1, A2, A4, and A5 and put them in to our critical path formula. And the other activities, we're assuming they're not changing. So they were previously 1 for all the other 3. We're assuming they're still 1. Okay, so we wanted to find the critical path and the max time, so we're simply calling that formula from before. And we're going to run this 10,000 times. So we're going to have each time, it's going to dump into this complete empty list the maximum time, what the critical path number is, and we can actually track what it gives us in terms of the times for A1, A2, A4, and A5. So I'm going to run that. Goes quick. And then what I'm going to do is say, okay, take all this information that was in this complete list and just turn it into a data frame or a table so that we can see it better. Okay, so rather than just a string of numbers, have it in columns where I have a column for the maximum time, a column telling me what the critical path was, and the amount of time that was randomly generated from the beta distribution for those activities. If I run the code called head parentheses, it'll give me the first 5 of our 10,000 simulations. So we call this complete table and then just give me the head of it. Just lets me see at a glance that everything is working properly. So notice here in the first simulation, the quickest that the house could be done is in 10.68 months. The critical path was critical path number 1. And you can go back, right? We can see from our scenario, path number 1 was A1, A2, A4, A7. It randomly generated a time for A1 where A1, the designing the house, took 3 months and A2 took 2.4 months. So you can see here where it is more pessimistic on these activity 1, 2, 4, and 5. Then the earliest we can complete the house is going to be longer. In comparison, in simulation number, well, it's row 1 here. Remember, it starts at 0, so 0, 1, our second row is index 1. The quickest the house could be done was 7.9 months. The critical path became path number 3. A1, A2, A5, A6, A7 no longer was activity 4, slowing everything down. So if you take a look, activity 4, notice how in the random number generator, where we're looking at activity 4, we said here, best case scenario 1 month, worst case scenario 5. When activity 4 took less time, then what happened is the critical path changed and we could finish the project much sooner. So we are allowing for variability in some of the activities, not all of them here, just 4 out of the 7. And we're using a beta distribution to represent that variability. The beta distribution has a best case scenario, a worst case scenario, and a most likely. Our formula here was from the beta distribution, so you can just take that as is. And our simulation then pulled those best case, worst case scenarios, use that to generate a time for the 4 activities, and then repeated the process before in terms of finding maximum time and critical path. If we do that 10,000 times, we can actually turn it into a graph. So we're going to use Seaborn, which we called SNS, to create a plot, a histogram. And it's a histogram to show us this column here of max time. So complete underscore table, give us the column called max time. So hard bracket says this is the column I want, and the quotes say this is the name of it. We can put in a hard black line here, that's this plt.axv line, add a vertical line, and make it nice and thick, x equals 10, or sorry, make it nice and thick with a line width equals 4, color equals black, and we're putting it here at 10. The reason we've put it here at 10 is because we want to know if we promise the customer we're going to finish the house at 10 months, what's the likelihood we're actually going to finish the house at 10 months? So what you can see here on the left of the black line is in 10,000 simulations, all the times we finished before 10 months. On the right, you can see all the times where we didn't finish in time. So we're trying to figure out whether it's reasonable to promise the customer that we're going to finish in 10 months. So this graph shows us that most of the time we're going to be good. And we can find the number. One of the reasons we ran 10,000 simulations is we can find of those 10,000 what percentage are less than 10, or we can find out what percentage are more than 10. So let's take our complete table, the max time column, and we are going to then take our complete table, and we want to know when the max time is less than 10. We're going to then count those and divide by the total number of simulations, which was 10,000. So of the complete table max time of that column, how many in that column are less than 10? Count them. That's what this code means. Take this max time column, find the less than 10 in that column, and count them, and then divide by 10,000. So what happens here is that 87.5% of the time we will finish before 10 months. Now the other thing we could do is we could find out how often the critical path is the path that includes that, is the first path, the one that has, if we go back, our critical path here of 1, A1, A2, A4, A7. So how often is that the sequence of activities that's limiting our abilities? And so we can do that as well as a calculation. That's what this is. So go to the complete table, find the column CP, that's the critical path, and then find how many in that table are equal to 1, count them, and divide by 10,000. We do that, and we get that 84% of the time, the critical path is that first path. We can, if you want to plot what happens with the critical path, you can do complete underscore table. That's our complete table name we gave it. And we can say do value counts and do value counts of CP. So what does this do? It goes into the column called CP, and it's going to count how many times in that column it has the number 1, how many times it has the number 2, how many times it has the number 3, and so on. And then we can sort it, right? So that way we have not the number of counts for path 3 and then the number of counts for path 2. Tell us it in order. That's the sort index here. And we'll call that CP count. And we do that so that we can graph it. So we take CP count dot plot, create a bar graph. That's the kind we want. Okay. And we're going to label the x-axis critical path and the vertical axis count. And then we use plt.show to create it. So here we can see that in our 10,000 simulations, critical path number 1 is the dominant path, more than 8,000 out of the 10,000. And then you can see the other path that dominates is path 3. So that's when activity 4 happens to generate a lower time. That then switches the critical path. But the main path is the first one. So try this. What if A3 has a completion time of 2 instead of 1? Find the completion time and the critical path with no variability. Okay, and then what if A3 has variability? A equals 1, M equals 2, B equals 3. So we're repeating the process before, but what we're going to do is we're going to add, first we're going to change A3, and then we're going to add variability to A3. So if we want to use this code, we already have our paths already defined. We already have our packages loaded, so we don't have to do any of that. We're going to take this command here where it gives us the max time and the critical paths, and I'm going to paste it down here. And what we're changing here is that A3 has a completion time of 2 instead of 1. So activity 3 here is no longer a 1, it's now a 2. Run that. Give me my max time. So now the soonest we can complete this house, it's still 9 months. Because activity 3 wasn't part of the critical path when we didn't have variability in the activity time. So critical path is still number 1, and it doesn't include activity 3. So if activity 3 is taking more time, it's not enough time to shift the critical path. And we still finish in 9 months. So we had slack of about a month when it came to activity 3, and so it doesn't change anything. But what if activity 3 had variability? So in this case, it's not just that it's going to be that it's going to take 2 months. What if it could, best case scenario, take 1, worst case scenario, take 3, most likely take 2. To do this, we are going to use our beta distribution. First, we're going to create our table. Okay, so I'm going to take this information I had before, these activities, A, M, and B, and I'm going to construct a new table. So I'm going to do this. And I'm just going to add in A3. We still have the variability for the others. And it's going to go 1, 2, and 3. Okay. And then I'm going to go back to the code I had before because I want to turn it into a table. And I can take the code exactly as written here and construct a new table. And I can show it. And so we should have a new table here, and it adds in A3. Now that we've added it to the table, we can then call it and call the information from the table. Now, we don't have to redefine our beta distribution here. We're just going to call PERT because we've already run it. We do need to create a new empty list for complete that we're going to populate. Just got to create a new spot for it, so add code. Okay. So we're just emptying out that complete list so that we can refill it. Then what we're going to do is we're going to take here our loop that we're running 10,000 times. and I'm going to put it here. I'm going to add a spot for it. Now what we need to do is we need to add in A3. And we're going to use, it's basically just calling the locations from that variable table. We just need to specify where it's going to get that information. So it's going to pull A3A, it's going to pull A3M, it's going to pull A3B, and it's going to use that PERT definition. So it's that beta distribution it's using, and it is going to then generate a random number for activity 3. So I'm going to run that loop. Now, I got a bit of a problem here when I ran this loop, is that while it created random numbers for A3, it's not including them when I do my max time and my CP. So I need to replace that 1 with an A3. And if I want to monitor what it is generating for the A3, I need to make sure that it is retained. So that append means add it to that empty list so that we can see it later. So if I just change by adding that 1 row, it doesn't help me any because I need to make sure it goes into the other definition for the critical path. So we have it here, A3, and now let's run it. All right, now let's see how we did. So we can, using the same methods we did before, we can take our information, we can turn it into a table so it's nice and easy to read. So we're going to copy that down. And tell me what it is. So I need to add it here, A3. All right, what am I missing here? Oh, I'm missing a comma. Then what we're going to do is say, show me the top of it so I can just see how it's doing. So we show the head. Okay. One, two, three. Capture our 5s here. Let's see what's happening. And we're going to then here, let's graph this. So let's see what happened. And our code. My apologies for the length of this video here. And so we can see here the distribution in this scenario. So you can see again, the majority are finished before 10 months. If you want to compare to a different time period, then just change this 10 to a different one. And if we want to find the probability that we have finished before that 10 months, then we can do our counts here. So here it was 87% of the time we were done before the 10 months. When we add the variability for activity 3, let's see what happens here. All right. Something is wrong with our code. All right, so A3A, A3M, A3B, A1, A2, A3, A4, A5, 6 and 7 are 1s. Calculate A1, 2, 3, 4. All right. Not sure what happened last time, but if you're getting weird things, just rerun. And so make sure you're going to rerun from complete equals list, so we have an empty one, and then rerun the loop. Now we can see that A5 has populated, which makes more sense. Let's rerun our graph. And let's rerun our calculation here. There we go. So here we have 83% chance that we'll be finished before 10 months. So you got to know enough to be able to look at it and say something's not looking right. Sometimes when you get those results like that, it's because you have defined something one place and it's using that, and you went to define it as something else now. And so you got to rerun it. Worst case scenario, you go to run time, run all, and it starts at the beginning and it runs through everything. And that way, if it doesn't have a definition, doesn't have a value for a variable, it will catch it through all of them. So you can go through. Lastly, here we can see if there's been a change in the critical path. So, sorry, mind the scrolling here. We can look at the percentage of time that, actually, we'll skip that. We'll go here and let's look at a graph. So let's do here, add code. Okay, one more try here, add code. Copy this. If you want that percentage calculation, you can capture that one above. I'm just going to get the graph here. So we'll just go down and we'll do this here. Find the counts of the different critical paths. And then we want it to turn it into a graph. So we'll just copy this code right here. And here. And run that. So we can see here that multiple critical paths are possible when we add in that variability. It swings equally rigidly between the critical paths 1 and 4, and even 2 and 3 are in play when there is that variability. So the key here is to recognize how variation in certain activities can have a huge impact on the likelihood of you finishing a project at a certain time. And so you run these simulations to say, okay, well, what if the variability is a little different than we anticipate? What impact does it have? So I encourage you to try this again and figure out what if the activity 3 has even more variability. So it goes from best case scenario 1, worst case scenario 5. The most likely is still the same, but there is now a much bigger time for activity 3 in the worst case scenario. What does that do to the likelihood of finishing the project within 10 months?